remote clinical ambulatory assessments for people with multiple sclerosis and Parkinson's disease. Welcome, Victor, and the floor is yours.
Awesome. Thank you so much for the great introduction. First and foremost, want to thank the University of British Columbia for having me here for the seminar talk. And I'm so glad that everyone's here to join me on this final day. Perfect. So thank you for the good introduction. I'll just quickly go through some things about myself as well. But the title of my talk today is The Use of Machine Learning for the Prevention of Occupational Injuries. So a little bit about myself, let's expand on some things that were talked about. I received my Bachelor of Kinesiology and Master of Science from the University of Toronto, studying with Dr. Tyson Beach. And the main thing that I was looking at was studying the effects of augmented feedback and its effects on lifting mechanics and its ability to reduce low back disorder risk factors. And the augmented feedback types included knowledge of performance, tactile cueing, and as well as using visual aids such as posters to influence lifting mechanics. So my PhD was at the University of Ottawa with Dr. Ryan Graham, again specializing in biomechanics. And my main thesis project, was to develop a fatigue estimation system that used inertial measurement units as in conjunction with machine learning, or ML, to be able to estimate fatigue in real time. Some side projects included looking at soldier survivability analysis using an IMU and machine learning, and as well as gait analyses using smart instrumented insoles. So that brings me to my postdoc today, where I'm working fully on that project with the University of Ottawa and Celestia Health Systems, where we aim to provide clinical gait and jumping assessments at home or in the wild using smart instrumented insoles. And our goal is to be able to provide users and as well as clinicians a way to be able to track the progression or regression of their gait abilities at home and without having to come into the clinic. Aside from that, I'm also an avid badminton player and a dog owner. So today I was invited here mainly to present my findings from a scoping review published in Applied Ergonomics in 2022, and it was titled The Role of Machine Learning in the Primary Prevention of Work-Related Musculoskeletal Disorders. So this is also a chapter for my PhD thesis, and we have actually made this work open access, meaning it's free for anyone to look at. So please feel free to scan it and read it on your own time, and I'll also put this code up at the end as well. So the very first thing, a bit of an icebreaker question, I'll have a chance to kind of ask everyone in the room, what is your experience with machine learning? And some of the answers I have here that you might see in front of you are on the screen. So I'll give you a minute, see if you can quickly respond, and we'll touch base on some of these answers. Awesome. So almost 70% of you have responded so far, and kind of the leading answers I'm seeing is that I either don't know what machine learning is, or I've never implemented it or used it to my knowledge. Okay, so thank you so much for your feedback. That's really helpful to know. That's a good starting point. So we're going to go into it a little bit. I'll kind of give you a quick overview of what machine learning is. I'm not going to sit here and pretend like I'm an expert, but I will give you my best explanation of how it works. Okay, so thank you so much for responding. So what is machine learning? Well, alongside robotics, machine learning is consistently considered a branch of artificial intelligence. Okay, so again, machine learning is considered a branch of artificial intelligence where other branches would be considered as being robotics or natural language processing. So a formal definition that is commonly given for machine learning is that it's the use of algorithms to optimize performance criterion using training data or past experience. Maybe an easier definition to swallow is that it is applied statistics, and it's commonly used to learn patterns in your data set and then use this understanding of the patterns to make estimations or classifications on new and unseen data. So a key thing about this definition is that it's actually using a lot of applied statistics, and a lot of methods that are being used in machine learning have been around for decades and even in centuries. So some methods would include very simple learning algorithms such as linear regression or logistic regression. These can be now leveraged to be used in a new manner because of certain things that have changed in the past decade. One thing is that we're able to collect a lot more data, which means that we have access to bigger training data sets that we can rely on. Another thing is that we have increased processing power. So we have the computational power to be able to learn from these data relatively quickly, but perhaps more importantly, be able to run these models on our mobile devices or cloud-based servers. So we're able to apply some of these methods that have been around for a while, but relatively quickly and oftentimes in near real time. So that's a big part of why machine learning has a relatively big boom in the past decade. It is using a lot of methods that we've actually developed for a while now. So there's three main types of machine learning that we'll quickly gloss over. The first of which is unsupervised learning. And an easy way to think about unsupervised learning is that's typically used for exploratory analyses. In this sense, we actually do not know a lot of the patterns that exist in the data set. So if we have a brand new data set, we don't know too much about it. One good way would be to use unsupervised learning methods to find patterns that may exist in there. So one method would be to cluster the data points. Right here, we have a very simplistic example where there's two dimensions of each data point, and we're trying to find similarities in them. A common method is to use cluster analysis, and a lot of them are typically based on the distance between data points or their similarity. And common methods that are used would include k-means clustering or hierarchical cluster analysis. There's many other types as well that do not rely on distance or similarity metrics, such as Gaussian mixture models or latent Dirichlet allocation. But these are commonly used, especially in the field of injury prevention. The key thing here is that, of course, it doesn't kind of give us direct insight into the entire data set, but allows us to go into further identification or investigation. So if we see that we have, let's say an example here would be that we have data points on individuals. We see that there might be different clusters of people or different subgroups of individuals. Then we can look in between them to see what may be differing about them and see if there's any commonalities within those individuals. So it gives us an ability to look in a data set and find patterns that we didn't know existed in the first place. And that's the first type of machine learning that we'll talk about. It's unsupervised learning. The second type is maybe what is more commonly considered as, what you might more commonly see is called supervised learning. So very, very simplistically, what we're typically doing is to train a model on our known or labeled data set. And then we use this model to subsequently make classifications on unseen data. And it can be either categorical or it can be an estimation on unseen data. So a continuous value, and in which case it would be a regression problem. So some key definitions here is that our input data is the information that is known about the sample or data point during the training part of it. And it's also known during the time when you make a prediction. The label, or the other words, the ground truth, is information about a sample that is given to you at the beginning and then is not known when we're trying to make a prediction. That's actually the label, or the ground truth is what we're trying to predict. So key thing to keep in mind is that both the inputs and the labels can be a category or a continuous number. Okay, so I just talked a lot, but I'll give you a quick little demonstration or like a quick little simple example of how it might work. So what we might have here is maybe our problem is we want to be able to classify what fruit we have in front of us. And this is our data set that we're training off of. We know everything about this data set. We know the mass, the volume, and the type of fruit that's in front of us. What we might do here is then train a supervised machine learning model. And there's many models that we may use, such as a simple linear regression model, or something similar as well, such as a support vector machine. And then we could also use something a little bit more complex, such as a deep neural network, to accomplish the same thing. The key thing that we're doing here is we're trying to learn the relationship between mass and volume, and that relationship with the type of fruit, so that at the end goal later on, we can make a prediction on unseen data. We're now trying to figure out what the label is, what fruit, if we have the mass and the volume. And that would be the goal of this machine learning model, to make that prediction. This is supervised because we are essentially, in a way, supervising the training process by giving it the known type of fruit to begin with, to now, when it sees unseen data, it's able to make a prediction on that. One thing I want to switch around is that this end result is categorical, so we're making classifications on our data point at the end. And This could also be switched around. It can also be making an estimation on a continuous value. So let's say, for example, we know the type of fruit and we know the volume, and we're just trying to predict how heavy it is. That might be a regression problem, and in which case, the mass is our label or ground truth that we're trying to figure out, and the volume and type of fruit would be the input into our model. Okay, so in a very simplistic manner, this is how supervised learning works, and there's a variety of models that can be fit in here to be able to help solve our problem. Okay, so that's supervised learning. That's a second type of machine learning that we'll talk about today. The third type is the one that we won't dive too much into, since it's only found to be included in one study in this scoping review, and that is reinforcement learning. And the gist of it is that we want to use this to determine an optimal action sequence to be able to maximize return during using feedback. And this is commonly used in robotics. So typically what we will have is we have an agent that performs an action in any direction within an environment, and they are trying to look and maximize the reward signal and use feedback about their current state to be able to determine what actions to take that may be able to maximize this reward signal. Okay, so reinforcement learning, again, is our third type, and it's situated between supervised and unsupervised learning. But unfortunately, it hasn't been used too extensively within the field of injury prevention so far. So before we kind of move on to the scoping review, let's quickly take a look at where does deep learning fit, as we might hear this term come up a lot in literature or in the news. Well, by definition, an artificial neural network with three or more layers is considered a deep neural network. So that's when we're performing machine learning with an artificial neural network with 3 or more layers by definition. Deep learning is helpful because it's able to be used end to end. It automatically extract and determine which features are most suited or most related to our end result or the thing that we're trying to predict. The key reason why it's so popular and used so broadly is because it's actually suitable for all three types of machine learning. It's used in unsupervised learning, it's used in supervised learning, and it's perfectly suitable to use for classification and regression problems, and as well as within reinforcement learning. So the key thing here is it's suitable for many different types of problems, which is why deep learning methods are often used in the realm of machine learning. But is it better than shallow methods? Well, one key thing to keep in mind is that some of the shallower methods, such as linear regression or support vector machines, are more interpretable, so we can actually understand how it's coming to its decisions compared to a deep neural network. Another consideration is that deep neural networks tend to take more time to train and are more computationally expensive to run. So if you get the same result using something lighter, we might prefer that. Another thing to keep in mind is that there's the no free lunch theorem will tell us that most of these algorithms are relatively equivalent when averaged across all possible problems. So the best model for a given problem is typically dependent on the problem itself. So before we kind of dive into the scoping review, a really quick question. Have you had any hesitations in using machine learning to make any data-driven decisions in your work or studies? Okay, I wish I had a chance to kind of ask a bit more detailed about what your hesitations may be, but maybe that'll come up in some of the questions later. But we see it's relatively split, the results here. Let's see, it's almost 50-50, which is good to know. Well, as you can imagine, several years ago, a lot of people definitely did have more hesitations. So the purpose of the scoping review that I've done here is to determine how machine learning has been used so far in the primary prevention of work-related musculoskeletal disorders. So this was the purpose of the scoping review to determine how it was used, and we looked at all the large literature databases. When we found our results, I'll go over the results in a second, we actually organized all of them by using the repeated sequence of work-related musculoskeletal disorder prevention framework by Van der Beek and colleagues in 2017. They had 6 steps in this framework, and we organized it using these 6 steps. The first of which was the look at the incidence of MSDs, and this is to determine the extent or the severity of MSDs using epidemiological data. The second step was to look at the risk factors for MSD by using epidemiological data and cross-sectional studies. The third step was to determine the mechanisms and pathways for MSD development. Step 4 is to develop an intervention that targets known risk factors and mechanisms. Step 5 is to evaluate the efficacy and effectiveness of the intervention. And step 6 is to implement the interventions while considering the process, the cost effectiveness, and the fidelity. So, another quick poll. Which of these 6 steps of the framework do you find most closely aligns with your field of work or study? I feel like to get a good sense of where you might be working closest to. If you have more than one, then just click the one that you think you spend a bit more time looking at. Okay, cool. Thank you so much for answering so far. We're halfway there. So far, it looks like we have the most people looking at step 2, the risk factors for musculoskeletal disorders. Which makes sense given the program that some of you are in, or a lot of you are in. I'll just give you another second because I'm really interested in these results. So looks like 40% of you are saying that you're most closely aligned with looking at the risk factors for MSDs. The second would be looking at the evaluation of interventions, and then followed closely by the incidence of MSDs. Okay, so it's a really interesting thing to hear about, and we'll take a look and see how machine learning has been used to improve some of the research and preventative efforts in these fields. Okay, so thank you so much for answering. Okay, so the scoping review, we looked at all large databases and we limited it so that it went back to 1990. It was in English and as well as original research only, so primary studies only. So a limitation is that the scoping review excluded conference proceedings, theses, and non-English articles. So we had 4,600 articles for screening, removed the duplicates, screened 3,200. We found that about 260 of them were okay for being read in full text for their eligibility, and we kept about half of those. So 130 studies were included in the scoping review, and I'll go over exactly what kind of studies were included in each of the steps. Some key things that you're perhaps not surprising is that we had more publications and a big boom in recent years. Notice here that the data points kind of ends in 2021 because this was published or submitted midway through 2021. Some of the more common applications of machine learning, we have here in the clear bar that classification was really common in our step 1 and step 4, whereas we had regression was quite common and used in step 3, and clustering algorithms were used in step 2 quite frequently. And we'll go over exactly what was being done in each of these steps. So for step 1, the goal of step 1 is to determine the incidence of MSDs. And there are 14 studies that we found that were directly aimed towards improving the incidence of studying the incidence of MSDs. So machine learning was most commonly used to auto-code worker compensation claims. So we know that coding these claims is quite challenging and very time-consuming. So it was able to be used to determine the injury types, the causes, and severity automatically. And naive Bayes classification was the most common type of machine learning algorithm used here. Some key reasons for why the researchers use this is because it's quite interpretable, and it also provided prediction confidence to be able to flag for manual review. So it's kind of easy for them to kind of determine what things needed to be looked at in further detail. So one notable contribution I found from this step was a study from Harbour and Leroy, where it's called the feasibility and utility of lexical analysis for occupational health text. And they used natural language processing, or NLP, lexical analysis, using a Stanford part of speech tagger to be able to analyze 89,000 free text records. So they did not have to numerically code any of these fields. They were able to kind of process it directly in free text. And what they did is they actually used terms found in the Unified Medical Language System, and they looked at the common exposure, health effect, and injury or exposure-injury relationships, and were able to reveal them. They analyzed them as a couple different ways. The first of which was to look at term frequency, how often it came up, the co-occurrence, the combinations in their frequencies, the coverage, so the cumulative number of instances covered by a set of terms, and as well as classifying the injuries to one of 8 labels that they decided, such as injury, medical, technical, causal, whatever. And some of the output that they had from their model included being able to determine how often a word was used, which is relatively straightforward, and then also be able to determine the pairs that were most frequently used as well. Okay, so this allowed them to be able to find common themes within a large database of just free text with minimal effort. Okay, so this is a very notable contribution because they were able to process a large amount of data that would have taken more manual hours to be able to perform. So moving on to step two, the second step was looking at risk factors for MSDs. And this actually was probably the most relevant field for most of you in the room and online. And we found out there's actually 33 studies in the scoping review that were included for this. And there is very diverse input data that were used in the machine learning models, which include questionnaires and interviews, so text input, injury records, radiographs, physiological measurements, biomechanical measurements, as well as ergonomic assessments. There were three distinct approaches that I saw within this step. The first of which was for unsupervised clustering, where they retroactively looked at data sets and looked for subgroups within them. And a really helpful thing about this is that the domain knowledge was not imperative. They didn't have to know too much about a specific industry or a job type to get information about some of the potential risk factors here. The second type was that they identified predictors of risk factor magnitude. So they use either clustering or regression. And then they use other data to be able to estimate exposures to these known risk factors. For example, whole body vibration is a known risk factor for low back pain, so especially people who drive vehicles or heavy machinery. And they want to use more accessible data sources to be able to predict the magnitude of which you would get exposed to whole body vibration. And the last approach I saw that fit in the step was to classify job risk. So they trained machine learning models using job and associated injury rates to predict if a new job was considered to be high or low risk. Okay. So if we go dive into that first method, the unsupervised clustering, we'll kind of talk about what some of these studies did and how it was kind of helpful for them to be able to enter a new space without knowing too much about it. So they might have a lot of information about the workers or the jobs themselves. And their first step would be to look to cluster these data using an unsupervised algorithm to see if there are subgroupings where data points, jobs, or workers that are more closely related to each other. Then they're going to compare between these identified clusters to see if there are WMSDs within these clusters. So for example, if the blue has a little bit more on average compared to the gray cluster, which has less than, again, the yellow cluster, then there might be some differences in the amount of WMSDs between the clusters. If there was no differences in them, then you'd monitor the development over time. So they just keep those subgroups, monitor how it may change over time. After that, if they were able to find that certain clusters were more likely to have a WMSD within a certain time frame, they would actually compare features between these different clusters. And by features, I'm talking about data points that are not related to, or not directly related to WMSDs. Maybe it's how many hours they work, or how many hours they spend lifting something, or maybe how often they spend driving or seated at a desk, etc. So they're going to compare different data points or descriptors about their jobs to see if there's anything different between them. If there is something different between them, they can look at those features and determine if they are potential risk factors for WMSD in the future. And if there's nothing that's different between them, even though that they have different injury rates or different injury prevalences between the subgroups, then potentially there's no risk factors that are present that's being collected, or there's insufficient data. And that allows us to be able to look further and deeper into these subgroups. One key thing that I want to mention is that through this process, these researchers did not determine any type of causation, just merely association. So let's say they were able to determine greater time standing was more linked to low back pain reporting. They weren't able to establish causation through these studies alone, but they are able to identify potential things to then take a look at with their further research. So again, a quick recap of this notable method that I saw in literature. They would take a data set of individual employees and or jobs, cluster these data, and take a look at the subgroups that may exist, and look to see if there's different injury prevalences within them. If there are, then they'll compare different features about them that they know. And if there are different features, then they can look further at them to see if these are related risk factors for WMST prevention or WMSTs. Okay, so this is a notable method where it's very exploratory. They don't know too much about the data set yet, but it can tell them where to look from this point forward. Okay, so that's for step 2. For step 3 is to look at underlying mechanisms. And there are 29 studies that contribute to this, and the primary type of machine learning used was supervised learning to solve regression problems. The key thing that I found here was that they were using machine learning to make biomechanical methods to study these mechanisms more accessible. Okay, so they were still studying the same mechanisms as they were in other biomechanical studies, but they're using machine learning to make it more accessible so that they can study it in the workplace, in the field, and not just limited to the laboratory. So this included developing machine learning models to estimate internal joint loading using kinematics only. So typically the way that this is done is that we use force plates with ground reaction force, and then use inverse dynamics to estimate the joint loading in all 3 dimensions at the joints going up the chain. Of course, the force plates are very expensive, require lots of processing and expertise, so it's a lot more helpful if we can try to estimate this using kinematics or movement of our body, which is much more easily attainable. Another one was that they estimated EMG or muscle activation output using kinematics only. This was a common one. Another method or another application of machine learning was to develop models that would estimate the ground reaction force, as shown here in the blue vector, using only kinematics. So just based on how someone's landing on the ground for their walking, running, etc. They were able to do their best to estimate what the ground reaction force would be. We had some studies actually look at estimating the grip exertions or how much grip force they might be using by using videos of people's facial expressions. So instead of actually measuring how much hand grip they may be using, but instead of just developing models that are able to use computer vision to then estimate, based on your expression, how much force you may be exerting. And last of which is developing models to estimate mechanical energy expenditure using smart insoles as well as computer vision. So looking at the mechanical power or energy expenditure throughout their work tasks, they're able to estimate when someone may be getting more tired or maybe more in need of a break. So one of the most notable contributions, especially within the realm of biomechanics, is the development of markerless 3D motion capture. So motion capture traditionally has been done in laboratories only and require these retroreflective markers that are placed on the skin all around your body to be able to capture your movements in 3 dimensions to a high degree of accuracy. Markerless motion capture uses discriminative learning to be able to infer the shape, pose, and the location of the body in 3D space using just RGB video, so red, green, blue video, so 2D video. And it's doing so by training machine learning models using large databases of body parts, joints, and pose examples. So the benefit of being able to do this is now biomechanical analyses can be very accurate, so less than a centimeter and less than 3 degrees of error. They can do so and track many individuals at once without markering them up. And it can also be done in many different environments, so it can be taken outside with relative ease compared to being constrained in a laboratory. So not only is this helpful for studying biomechanical mechanisms of injury, but this is also useful for other like industries such as filming, things for animation, for example. Okay, so this is one of the notable contributions, and the company that's doing that was Thea. And the 4th step is the most common step for the application of machine learning, and this was the development of interventions, where many different unobtrusive devices were used, such as IMUs in watches and phones, and instrumented pressure insoles, heart rate monitors, and cameras. One of the key things that machine learning was used for was to quantify worker risk in real time. So, for example, looking at safe versus unsafe postures, detecting the performance of unsafe tasks, obtaining the inputs for ergonomic assessments, such as the rapid upper limb assessment, and also estimating and classifying the fatigue state to be able to give breaks to workers before they may be getting an injury or an accident. Other methods, other applications of machine learning included performing a pre-employment screen, to estimate worker risk using anthropometrics or body measurements, movement strategies, and ergonomic assessments and questionnaires. So risk in this situation was quantified as load exposure level, strength capacity, and injury risk indices. And the point of these pre-employment screens was to determine which workers needed more additional training to prevent injuries in the first place. So one really notable contribution of machine learning to development of interventions would be human activity recognition, which is a very important for many different fields, even outside of injury prevention. But typically what will happen is that IMU data is being tracked from a device, body-worn device such as a smartwatch, which contains accelerometer, gyroscope, and magnetometer data. And this is used to train a machine learning model that is going to be labeled with the true task they're performing. So for example, this might be information about someone walking. This might be information about someone pushing. This might be information about someone lifting something. Maybe this is information about someone running. And the machine learning model is able to look at these time windows and determine that this person is likely doing what task. So that way we can know what is going on, even just using the motion data. So it's able to predict the tasks such as walking, taking stairs, so activities of daily living, but can also be used to estimate which or classify which tasks are being performed at work, such as lifting, pulling, pushing, as well as carrying something. And beyond just determining what task, can also be used to determine the manner in which a task is being performed, such as if someone's lifting with a squat lift or using a stoop lift instead. So why is this so important to development of WMST prevention interventions? Well, it's an intermediate step for determining the time spent in performing a task, determining the time spent in risky postures that are more injurious, performing task-specific analysis that might be, let's say, specific to lifting, and that could be useful for estimating the fatigue while lifting or calculating the inputs for ergonomic assessments. So machine learning is used here to be able to estimate or classify the tasks that they're performing just using their motion data. And the awesome thing is that oftentimes these motion data don't even really need to be processed before use with human activity recognition. So for step 5, the evaluation of interventions, there's only 6 studies that contributed to this. And there's many different things that they're used to evaluate the interventions. One way is to assess the usability and acceptability of the interventions. Another was to help develop a scoring system to rank the intervention effectiveness, as well as evaluating the techniques to classify risk factor exposures, and as well as use changes in kinematic and muscular load to predict MST risk post-intervention. So one notable contribution was the development of this cyber-physical virtual training environment by Akanmu and colleagues in 2020, where they developed a construction-based training environment, and they used reinforcement learning, an actor-critic reinforcement learning method, to be able to determine the knowledge and skill gaps of the users, and then adapted the contents and delivery of the actual feedback given in this environment based on the individuals themselves. And this entire time, the usability and acceptability of the intervention was being evaluated by using the user feedback within the environment. So this was the only study within my scoping review that actually employed reinforcement learning directly. Moving on to step 6 for the implementation of effective interventions. So no studies actually contributed directly to this step that we found. It's likely because contributions were novel and aimed at affecting earlier framework stages. So it is an opportunity to implement machine learning approaches, and it has already been starting to be done in other fields, such as in behavior change interventions. So to give a quick summary of the scoping review, in the first step, there's 14 studies, and one of the key ways machine learning was used was to auto-code worker compensation claims. The second step was 33 studies, and that was a common method was to use clustering algorithms to identify subgroups and data sets. And then they can look at comparisons and features between the subgroups to see if any of them may be associated with WMSTs. The third step was typically using machine learning models to perform regression to estimate the outputs of biomechanical measurement tools and modeling. The fourth step had the most amount of applications of machine learning, where 48 studies were found, and it was typically used for performing classification regression to enable real-time risk monitoring in the field. For step number 5, there are 6 studies where there's the classification to support evaluation of interventions, and no studies were found for the implementation of interventions. Okay, so obviously a lot of you might be thinking, well, this happened, my scoping review came out in 2022, so obviously a lot has happened since then, so it's important to consider innovations that have come about since then. Now, I've obviously not had the time to perform another scoping review, but one key thing that's happened since then is that there has been the introduction of ChatGPT in 2022, which came out the same year as a scoping review. And it was a huge innovation as a large language model and a huge innovation in natural language processing as well, partially because it understands context as well as being able to maintain long-range dependencies in the conversation. So indirectly, ChatGPT and other large language models like it have helped in research by assisting with writing, coding, stats, and anything of the like. However, many organizations with sensitive data, which includes most of the data that I think you will be working with, they're not willing to kind of share these data with a large language models like this, as there's many concerns over their storage and retention of the data, accidental exposure either back to you or to other people, and as well as unintended sharing. So for example, some LLMs may actually use some conversations and data shared with them to train and update their models. So as such, most organizations have created regulations over what information can be used with large language models. That being said, machine learning can still be leveraged in the fields that we've discussed here. And most commonly is to do so by developing your own machine learning models, which is typically the kind of stuff that was presented in the scoping review. The key reasons why is because you can have full control over the data and make sure that either you can encrypt it or make sure that never leaves your controlled environments. By doing so, you will also have less restrictions from the regulations. And last but not least is that you can customize and adapt these models for your own problems and data set, which actually may lead to better performance for your needs in the first place. Okay, so lots has changed and it's made a big impact on a wide range of industries and fields. But at the end of the day, especially when we're working with sensitive data, we tend to want to develop our own models in-house to be able to have full control over what's happening, who gets access to these data as well. Okay, so the last kind of question I will ask you is that, has any of this information presented in the seminar make you more or less open to implementing these techniques in your work? So thank you so much for answering. Looking forward to hearing your questions. Awesome. So far we have 30 or so people. Oh no, like half of you have responded so far. It seems like most of you are maybe more open to it. No change for a lot of you as well, a third of you. And some people, one person may be less open to it, which is totally understandable. Okay, so thank you all so much for attending. I really appreciate you being here and being good listeners, and I'm looking forward to hearing your questions.
Great. Thank you